Tonight, we're going to talk about light, something so familiar that it barely feels like a scientific object at all, and yet something our intuition quietly misunderstands at almost every level. You've heard this before. It sounds simple. Light lets us see. Light travels fast. Telescopes collect light. But here's what most people don't realize. Almost everything we think we know about what it means to look at the universe breaks down the moment scale enters the picture. Light does not just show us things. Light delays them. Light filters them. Light replaces direct experience with something far stranger. To anchor this immediately, we need to accept a scale that does not behave like distance in everyday life. When we say that light from a distant galaxy has been traveling for billions of years, that is not a poetic exaggeration. It is not shorthand. It is a literal statement about time, motion, and causality that has direct consequences for what we can know. By the end of this documentary, we will understand why looking farther into space means looking backward in time, why even the most powerful telescope does not show the universe as it is, and why the James Webb Space Telescope forced scientists to confront limits that were not expected, limits not of technology, but of intuition. If you want to continue calmly and without shortcuts, stay with us. Now, let's begin. We start with something deceptively simple, seeing. When you look at an object in front of you, it feels immediate. Your eyes open, light enters, and the object is simply there. The delay between reality and perception feels non-existent. For everyday distances, this intuition works well enough that we rarely notice its failure. But even across a room, light is not instantaneous. It travels at a finite speed. The reason this does not matter to us is not because the delay is zero, but because it is small enough to ignore. At human scales, our brains treat light as immediate because the delay is far below the threshold of perception. This is the first intuition that will not survive what follows. Light moves fast, about 300,000 kilometers per second, but fast only has meaning relative to distance. Across a room, the delay is less than a billionth of a second. Across the Earth, it becomes noticeable only with precise instruments. Across the distance to the Moon, light takes a little over 1 second. Already, seeing is no longer simultaneous with now. We repeat this because repetition is necessary. When you look at the Moon, you're seeing it as it was 1 second ago. Not metaphorically, literally. If something were to happen on the Moon right now, you would not see it until the light had time to reach you. This does not feel disturbing yet. 1 second is still close to now in human terms. Our intuition stretches to absorb it. So we stretch again. The sun is about 8 light minutes away. When you see sunlight, you are seeing the sun as it was 8 minutes ago. If the sun were to suddenly disappear, which it will not, the Earth would continue to receive sunlight for 8 full minutes before darkness arrived. We say this again, slowly, because the consequence matters. The sun you see is not the sun that exists right now. It is a record, a delayed signal, a message sent through space. Still, this remains manageable. 8 minutes fits inside human experience. We can wait 8 minutes. We can imagine 8 minutes. Now we move beyond where imagination remains reliable. The nearest star beyond the sun is over 4 light years away. Light from that star has been traveling for more than 4 years before it reaches Earth. When we see that star, we are not seeing its present state. We are seeing an archived version, frozen years in the past. 4 years, then 10, then hundreds, then millions. At this point, something important happens to intuition. Distance stops behaving like space and starts behaving like time. Looking farther away does not just mean looking farther out, it means looking earlier. This is not a trick of language. It is a structural feature of the universe. We repeat the idea because it resists acceptance. Telescopes do not show us distant objects as they are. They show us distant objects as they were, when the light we now receive first began its journey. So when we build a more powerful telescope, we are not simply increasing magnification, We're increasing delay. We're extending our view deeper into the past. This is where the James Webb Space Telescope enters the story, but we're not ready for it yet. First, we need to understand what light actually carries. Light is not a picture. It is not a surface image peeled off an object. It is electromagnetic radiation emitted or reflected under specific physical conditions. When light leaves an object, it carries information about temperature, composition, motion, and structure, but only at the moment of emission. Once emitted, that information is locked in. Light does not update itself. It does not know what happens next. This means that every photon arriving at a telescope is a historical document. Some are recent, some are ancient, all are incomplete. Again, we repeat this because intuition resists it. We do not observe the universe directly. We intercept signals that have survived long journeys through expanding space. Now, scale enters in a way that cannot be visualized. The observable universe is about 93 billion light-years across. This number already feels abstract, so we translate it. Imagine compressing the entire history of human civilization, from the first stone tools to now, into a single second. Light from the most distant galaxies has been travelling for a time span equivalent to several lifetimes of that compressed second, stacked end to end. Even this analogy collapses under the weight of the number, so we discard it. Instead, we accept something simpler and harder. There are regions of the universe whose current state we can never observe, because their light has not had time to reach us and may never do so. This is not a technological limitation, it is a geometric one. Telescopes do not pierce this boundary, they only approach it. When astronomers point a telescope toward deep space, they are not looking outward in the everyday sense. They are selecting older and older layers of cosmic history, stacked by distance, filtered by time. This is why deep-field images look strange. Galaxies appear distorted, red, irregular. This is not because early galaxies were poorly behaved. It is because the light reaching us has been stretched by the expansion of space itself. We pause here, because something subtle has happened. We have not yet talked about galaxies in detail, or telescopes, or cosmology, and yet our original intuition that seeing means observing the present has already failed. This failure is not dramatic, it is quiet, and it will continue. The James Webb Space Telescope was designed to collect infrared light stretched beyond what human eyes can see, precisely because the oldest light in the universe has been shifted into these longer wavelengths. Webb does not look for brightness alone. It looks for survivors' photons that have endured billions of years of travel. But before we talk about what Webb found, we need to understand what scientists expected to find. Expectations are models. Models are not reality. And when models fail, it is rarely because nature made a mistake. For decades, cosmological models predicted a gradual progression. After the Big Bang, matter cooled, atoms formed, gravity pulled gas together, stars ignited, galaxies assembled slowly over time. Early galaxies were expected to be small, chaotic, and primitive. This expectation was not unreasonable. It was built from known physics, tested locally, and extended carefully. It made sense. The problem was not that the model was careless. The problem was that intuition had been quietly extended beyond where it was reliable. James Webb did not violate physics, it violated expectation. And that violation only becomes disturbing if we forget what light really is, a delayed, filtered, incomplete message from a past we can never revisit. At this point, we pause again and restate what we now understand. Seeing is not immediate. Distance is time. Telescopes collect history, not reality. Every observation is constrained by delay. This is the ground we stand on before going any further. Because once we accept this, the discoveries that follow stop feeling shocking and start feeling inevitable. Once we accept that telescopes collect history rather than the present, another intuition begins to weaken. We tend to imagine the past as simpler than the present, less structured, less developed. This intuition comes from everyday experience. Children grow into adults. Cities grow from villages. Technologies accumulate complexity over time. It feels natural to project this pattern onto the universe itself. For a long time, science did exactly that. The early universe was expected to be smooth, hot, and nearly uniform. After expansion and cooling, tiny irregularities would slowly grow under gravity. Gas would gather. The first stars would ignite. Small galaxies would form first, then merge and evolve into larger, more orderly systems over billions of years. This picture was not speculative storytelling. It was grounded in observation. We see small galaxies today. We see mergers happening now. We understand gravity well. When these pieces were assembled into a coherent model, the timeline made sense. It sounded simple, but simplicity here was not a flaw. It was a consequence of limited information. Before James Webb, our deepest views of the early universe were filtered through instruments that struggled to see faint, distant, red-shifted light. The picture we had was incomplete, but it was internally consistent. Again, we repeat this slowly. The model worked because the data allowed it to work. James Webb did not arrive to overthrow physics. It arrived to fill in missing information. To understand what changed, we need to be precise about what early means in cosmology. When astronomers say they are observing galaxies from 13 billion years ago, they are not pointing to a specific location in space where the past still exists. They are intercepting light that left those galaxies 13 billion years ago and has only just arrived. Those galaxies do not remain frozen in that state. They continued evolving. They may have merged, transformed, or disappeared entirely. The only thing preserved is the light. This matters because light from the early universe is not just old, it is faint. It has been stretched by the expansion of space. Wavelengths that began as visible light arrive as infrared. Photons are spread thin across an expanding cosmos. Older telescopes could see parts of this light, but not much of it. Webb was designed to see more not by seeing farther, but by seeing differently. Infrared sensitivity allowed Webb to detect objects that were effectively invisible before. When it did, the first surprise was not a single object, but a pattern. Very early galaxies, far earlier than expected, appeared large, massive, and structured. This statement deserves to be repeated, because its implications are easy to exaggerate or misunderstand. Scientists did not find galaxies older than the universe. They did not find impossible objects. What they found were galaxies that appeared to have formed stars, accumulated mass, and developed structure faster than models had predicted. The disturbance was not emotional, it was structural. If galaxies were already massive and organized so early, then something in the timeline was compressed. Either stars formed more efficiently, gas collapsed faster, or our interpretation of brightness and mass needed adjustment. Each possibility is subtle. None involves new physics yet, but all of them strain intuition. We pause here to stabilize understanding. What Webb sees is not the universe breaking rules. It is the universe revealing that our sense of pace, how fast complexity can emerge, was based on incomplete evidence. To grasp why this is difficult, we need to think about time again, but differently. 13 billion years sounds enormous. It feels like enough time for almost anything to happen. But most of that time belongs to later epochs. The early universe was compressed not only in age, but in conditions. Density was higher, temperatures were higher, interactions were more frequent. When we project present-day rates backward, we assume continuity, but continuity is an assumption, not an observation. This is where intuition quietly fails again. We imagine the early universe as a slow beginning. In reality, it may have been a period of rapid assembly under extreme conditions. The key word here is may. At this stage, Scientists are not replacing one simple story with another. They are carefully separating observation from inference. Observation. Webb detects bright, distant galaxies whose light left them very early in cosmic history. Inference brightness suggests high stellar mass or intense star formation. Modelling. Translating brightness into mass requires assumptions about stellar populations, dust, and formation efficiency. Each layer introduces uncertainty. Webb did not hand us answers, it handed us pressure. Pressure forces models to adapt or break. Some early mass estimates were revised downward as models improved. Dust effects were reconsidered. Stellar populations in the early universe may behave differently than nearby ones. These adjustments matter because they determine how disturbing the findings actually are. But even after revisions, something remains. Galaxies still appear earlier and more developed than our simplest expectation suggested. This is the point where sensational language often enters public discussion. Words like impossible or rewriting physics appear. We will not use them because they do not reflect how science actually responds to pressure. Instead, science asks which assumptions were weakest. Perhaps star formation in the early universe was far more efficient. Perhaps dark matter halos collapsed faster than expected. Perhaps feedback processes winds, radiation, supernovae behaved differently under early conditions. None of these ideas are exotic. All exist within known physics. The challenge is not inventing new laws, but recalibrating how existing laws operate under unfamiliar extremes. We repeat this because it matters for intuition. Extreme conditions do not require extreme explanations. They require careful ones. Another source of tension comes from statistics. Webb's deep fields sample small regions of the sky. If we happen to look at an unusually dense patch of early galaxies, we may overestimate how common such objects were. This is not an excuse, it is a reminder of scale. The observable universe contains hundreds of billions of galaxies. Webb has looked at a tiny fraction. Even powerful instruments see samples, not totals. So what exactly changed after Webb? Before, early galaxies were mostly hypothetical extensions of later ones. After Webb, early galaxies became data points, not many, but enough to constrain imagination. This is an important distinction. Constraints do not dictate answers, they eliminate comfortable ones. The most unsettling aspect is not that galaxies formed early. It is that they formed early and fast, leaving little room for slow, gradual build-up at the very beginning. Here, we need to resist a familiar mental shortcut, the idea that faster means more violent or more chaotic. Rapid assembly does not imply disorder. Under certain conditions, systems can organize quickly. Think of crystallization. Under the right conditions, structure emerges rapidly and predictably. The analogy serves its purpose and ends here. In the early universe, gravity operated on denser matter than today. Distances were smaller, interactions were frequent, time intervals between events were compressed. If intuition tells us that complexity must take time, that intuition is built on present-day conditions, Webb is showing us a regime where those conditions did not apply. We now pause again to restate what we understand. James Webb does not show us anomalies floating in isolation. It shows us early galaxies that force a reassessment of pace, not possibility. The tension lies in timing, efficiency, and interpretation, not in broken laws. This distinction matters because it determines how we respond cognitively. Panic signals misunderstanding. Calm adjustment signals progress. At this point, the word disturbing begins to take a precise meaning. It does not mean frightening. It means disruptive to established intuition. Our intuition expected a long, slow dawn. Webb hints at a faster sunrise. The next step is unavoidable. If early galaxies formed quickly, then the first stars, the engines of light and structure, must have formed under conditions we do not yet fully characterize. And that takes us deeper, not into speculation, but into limits. Because there is a point beyond which even Webb cannot see clearly, not because of distance alone, but because light itself runs out. Before the first stars, there was no starlight to observe. The universe was dark, filled with neutral hydrogen that absorbed and scattered radiation. This period is not invisible by accident, it is invisible by nature. Understanding that darkness and how we infer what happened within it is where intuition will be tested most severely. There is a boundary where observation stops feeling incomplete and starts feeling impossible, not because our instruments are weak, but because the universe itself provides nothing to carry information forward. This boundary is not marked by distance alone, it is marked by absence. After the Big Bang, the universe expanded and cooled. Protons and electrons combined to form neutral hydrogen. Light, which had previously scattered freely, suddenly decoupled and began travelling unimpeded. This moment left behind a signal we still detect today, the cosmic microwave background. Beyond it, there is nothing older that light can show us. But that background is not the darkness we are concerned with yet. After this release of radiation, the universe entered a long interval with no stars, no galaxies, and no visible light sources. Matter existed. Structure began forming invisibly. Gravity worked continuously, but nothing glowed. This interval is called the Cosmic Dark Ages. The name is descriptive, not dramatic. It refers to the absence of luminous objects, not ignorance or mystery. We need to slow down here, because intuition often misfires. Darkness feels like nothingness. In reality, the universe during this time was active, dynamic, and evolving. It simply did not produce light that could travel freely to us. This matters because telescopes, no matter how powerful, cannot observe what does not emit or transmit detectable radiation. James Webb approaches this boundary from one side. It sees the first galaxies after light returned. It does not see the moment before. Understanding this boundary clarifies what Webb can and cannot disturb. The first stars formed when gravity compressed dense regions of hydrogen until nuclear fusion ignited. These stars were unlike most stars today. They were massive, short-lived, and intense. Their radiation began to change the universe itself. This process is called reionization. Neutral hydrogen absorbed high-energy light, became ionized, and gradually the universe transitioned from opaque to transparent again. This was not instantaneous. It took hundreds of millions of years. During that time, light from early stars carved out growing bubbles of transparency in an otherwise absorbing medium. This is important, so we repeat it differently. The universe did not simply turn on, it flickered. Pockets of light expanded, darkness retreated unevenly. When James Webb observes very early galaxies, it is seeing sources embedded within or near these bubbles. The light that reaches us has survived a hostile journey, passing through regions that could have absorbed it entirely. This survival introduces bias. We only see the brightest, most extreme early objects because they are the ones capable of punching through darkness. Fainter structures existed, but their light never reached us. This is not a flaw in Webb. It is a selection effect imposed by the universe. Again, we repeat what we see is not what existed, it is what survived transmission. This realization stabilizes something that might otherwise feel unsettling. If early galaxies appear unusually massive or bright, part of that appearance may be due to survivorship. Webb is sampling the visible tail of a distribution we cannot fully access. Still, even accounting for this, the timeline remains compressed. To understand why this compression is challenging, we need to examine how stars form at all. Star formation requires cooling. Gas must lose energy to collapse. In the early universe, heavy elements were rare. Metals in astronomical terms help gas radiate energy efficiently. Without them, cooling is harder. This led to a long-standing expectation. Early star formation should be inefficient. Yet Webb suggests rapid assembly. This tension does not imply that cooling failed to limit star formation. It implies that other mechanisms may have compensated. For example, higher densities increase collision rates. Larger gas reservoirs may collapse collectively. Radiation feedback may behave differently when environments are pristine. None of these ideas are speculative leaps. They are extensions of known processes into regimes we have not observed directly before. Here, we need to separate discomfort from contradiction. The models were built by extrapolating from nearby, mature galaxies. The early universe was neither nearby nor mature. Expecting perfect continuity was convenient, not guaranteed. This brings us to a subtle but critical point. Models are not predictions in the everyday sense. They are constrained extrapolations. They are only as stable as the assumptions beneath them. James Webb did not falsify cosmology. It exposed where cosmology had relied on untested intuition. We pause and restate again. There is a hard observational boundary set by the first light-emitting objects. Beyond it, light cannot carry information. Before it, structure existed without visibility. What we infer about that era comes from models, not direct observation. This distinction protects us from misunderstanding what we don't know means. We do not know because nature does not allow direct access, not because we lack effort or intelligence. To study the Dark Ages, scientists use indirect tools. One is the imprint left on later light. Neutral hydrogen absorbs specific wavelengths, leaving signatures in the spectra of distant sources. By studying these patterns, we reconstruct the distribution of matter and ionization. Another tool is simulation. Large-scale numerical models evolve matter forward from early conditions, constrained by known physics. These simulations are not guesses. They are calculations whose outputs can be compared to observation. Still, they remain models. This is where intuition often demands certainty too early. It wants a picture, a story, a clean sequence. Science resists this demand. The early universe is not a narrative we can watch unfold. It is a state we reconstruct probabilistically, with error bars and competing interpretations. James Webb sharpened those error bars. It did not erase them. The most important consequence of Webb's findings is not a new timeline, but a narrowed space of plausible timelines. Some versions of slow, gradual assembly are now less likely. Others remain viable with adjustments. This narrowing feels uncomfortable because it removes familiar options. Again, disturbance does not mean danger, it means reconfiguration. At this point, we should notice something else that has changed. We're no longer talking about individual objects. We're talking about populations, distributions, and statistical inference. This shift is necessary because intuition about single examples is unreliable at cosmic scales. One early massive galaxy is interesting. Many are constraining. Webb's early survey suggests that such objects are not singular flukes. They appear with enough frequency to demand explanation. Still, frequency itself is model-dependent. Converting detected light into counts of galaxies requires assumptions about luminosity functions, completeness, and bias. This recursive dependence is not a flaw. It is how science advances under constraint. We use models to interpret data, then adjust models based on that interpretation, then re-evaluate. Nothing here is unstable, it is iterative. The unsettling part comes from realizing how much of our previous confidence rested on untested assumptions simply because no instrument could challenge them. Now one can. We need to pause once more and stabilize. James Webb has not shown us the beginning of everything. It has shown us that the transition from darkness to light may have been faster and more efficient than we assumed. It has revealed pressure points where intuition had quietly filled gaps. The next cognitive shift follows naturally. If the early universe assembled structure quickly, then our sense of early and late needs refinement. Age alone may not correspond cleanly to complexity. This does not mean time is irrelevant. It means time under extreme conditions behaves differently. To move forward, we must let go of the idea that cosmic history unfolds at a uniform pace. Some phases are slow, others are compressed. Webb is forcing us to acknowledge that the opening moments of visible structure may belong to the latter category. And with that acknowledgement, a deeper question emerges not about what formed, but about how confidently we can translate light into physical reality. Because light, as we will see, is not a transparent messenger, it is filtered, distorted, and incomplete. Understanding those distortions is where intuition will be tested again. At this point, we have learned to be cautious about what light shows us, but caution alone is not enough. We need to understand how interpretation happens at all, because the disturbance introduced by James Webb does not come from raw images. It comes from the translation of light into physical meaning. When Webb detects a distant galaxy, it does not measure mass, age, or structure directly. It measures photons, their wavelengths, intensities, and distributions. Everything else is inference. This is not a weakness of astronomy. It is its foundation. The process begins with spectra. Light from a galaxy is spread into its component wavelengths, revealing patterns of absorption and emission. These patterns carry information about the elements present, the temperatures involved, and the motions of gas and stars. But here is the first point where intuition must slow down. A spectrum is not a fingerprint in the everyday sense. It does not uniquely identify a single physical state. Multiple configurations can produce similar spectral signatures. This is called degeneracy. Different combinations of age, metallicity, dust content, and star formation history can yield similar observed light. We repeat this because it matters. Observational data rarely map one-to-one onto physical reality. When astronomers estimate the mass of a distant galaxy, they are not weighing it. They are modelling how much light certain populations of stars would produce under assumed conditions. Change the assumptions, and the mass estimate shifts. James Webb pushed this process into unfamiliar territory. It observes wavelengths associated with stellar populations we have never seen directly. The earlier stars likely had compositions and behaviours unlike anything in the nearby universe. So when Webb detects bright infrared light from a very early galaxy, scientists must ask what kind of stars produce this light. If we assume they are similar to stars today, we may overestimate mass. If we assume they are different, we must justify how and why. This is not uncertainty in the casual sense. It is structured ambiguity. The disturbance arises because Webb forces these ambiguities into the open. Earlier instruments blurred them away. Webb resolves them enough to demand attention. Here, we need to restate the chain carefully. Observation light at specific wavelengths arrives at the telescope. Inference that light likely comes from stars of certain types. Modelling those stars imply a certain mass and formation history. Each step depends on the previous one. None are arbitrary. All are provisional. When early analyses suggested extremely massive galaxies at very early times, the first response was not alarm. It was scrutiny of assumptions. Could dust redden the light and mimic age? Could bursts of star formation temporarily inflate brightness? Could stellar populations be skewed toward massive, short-lived stars? Each question reduces tension without dismissing the data. This is where public narratives often diverge from scientific ones. The word disturbing sounds dramatic. In practice, the disturbance is methodological. It forces a recalibration of inference pipelines. We repeat this calmly. Webb did not surprise nature. It surprised our methods. To understand why this recalibration is non-trivial, consider how little direct access we have to early conditions. We cannot observe individual stars in these galaxies. We cannot track their motions. We cannot sample their gas directly. All of this must be inferred from integrated light, the combined glow of billions of stars compressed into a faint signal. This compression hides detail, it smooths variability, It amplifies model dependence. And yet, this is not hopeless. Astronomy has always worked this way. What changed is that Webb pushed inference into a regime where previous calibrations no longer feel secure. We pause here and re-anchor. Light is not reality. It is a message encoded by physical processes. Decoding that message requires models. Models carry assumptions. This is not a failure mode. It is a controlled process. The reason this feels unsettling is that intuition wants directness. It wants to believe that better telescopes mean clearer truth. In reality, better telescopes often mean more precise ambiguity. Another source of confusion comes from images themselves. Webb's images are visually striking, detailed, and sharp. This visual clarity can trick us into thinking the underlying interpretation is equally clear. But image processing does not add information. It rearranges it for human perception. Colours in Webb images are often assigned to represent wavelengths beyond human vision. These choices are scientifically motivated, but they are not literal. They are translations. Again, we repeat what looks clear may still be uncertain. This does not undermine confidence. It defines its scope. Now we confront a deeper intuition failure. We tend to think that uncertainty means ignorance. In science, uncertainty means quantified limits. When astronomers report masses, ages, and distances, they include ranges. These ranges are not hedges. They are measurements of how assumptions propagate. Webb tightened some ranges and widened others. It reduced uncertainty about what light exists and increased awareness of how many physical interpretations remain compatible. This is progress. The most persistent misunderstanding is the idea that science seeks final answers. In reality, science seeks stable frameworks that survive contact with new data. James Webb forced contact. At this stage, some early claims were softened, others were reinforced. The process is ongoing. This leads to a calm but firm boundary. We do not yet know the precise formation histories of the earliest galaxies. We know enough to rule out some simplistic scenarios, but not enough to settle on a single narrative. This not yet is not a gap to be filled with speculation. It is a boundary to be respected. We need to repeat this distinction because it prevents cognitive overload. Unknowns here are not mysteries waiting for revelation. They are parameter spaces waiting for constraint. Webb contributes constraints. Future observations will refine them. Now we take a moment to restate where we stand. James Webb delivers unprecedented light from the early universe. That light challenges assumptions about how quickly structure formed. Interpreting that light requires models that are now under pressure. The pressure is methodological, not existential. This is the stable frame. The next step in our descent is not deeper into uncertainty, but deeper into why these limits exist at all. Because even with perfect models, there is a point where information simply does not survive. This point is not imposed by technology, it is imposed by physics. To understand that limit, we must look at how the universe itself changes the messages it allows to pass through it. Not by obscuring them accidentally, but by evolving in ways that permanently erase certain details. That erasure is not failure, it is a feature of cosmic history. And understanding it will reshape how we think about what looking too far actually means. There is a point where interpretation is no longer limited by our models, but by the universe itself, not because information is hidden, but because it has been overwritten. To understand why looking farther back eventually stops yielding detail, we need to understand how information is erased in cosmology. The universe is not a passive container through which light travels unchanged. It expands, and that expansion does not merely stretch distances, it stretches information. When space expands, the wavelength of light travelling through it stretches as well. This process is called redshift. Light that began in the ultraviolet can arrive as infrared. Light that began as infrared can arrive stretched beyond detectability. This is not distortion in the everyday sense. No noise is added. no scrambling occurs. The signal is preserved in form, but diluted in energy. We repeat this carefully. Expansion does not corrupt light, it weakens it. At small scales, this weakening is manageable. At cosmic scales, it becomes decisive. As light travels for billions of years, it loses energy continuously. Each photon arrives carrying less information than when it was emitted. Eventually, light becomes so stretched that it blends into background noise. This is not a limitation of telescopes, it is a thermodynamic consequence of expansion. Even James Webb cannot recover information that no longer exists in usable form. This sets a fundamental boundary. Beyond a certain distance, which is also a certain time, the universe becomes observationally opaque, not because it blocks light, but because light fades into irrelevance. We pause here because intuition often frames this as a failure of reach. In reality, it is a failure of preservation. Now consider what this means for early galaxies. The earliest light that Webb detects has survived an extraordinary journey. It has been stretched, weakened, and filtered by intervening matter. The fact that we see anything at all already implies selection. Only the most luminous sources, emitting the most energetic radiation, can remain detectable across such distances. Again, we repeat detection is not neutral, or it favours extremes. This introduces a subtle but powerful bias. Our picture of the early universe is built from the brightest survivors, not the average population. This does not make the picture wrong, it makes it incomplete in a specific direction. Now we examine another erasure mechanism, one that operates not through expansion, but through interaction. In the early universe, neutral hydrogen was abundant. Neutral hydrogen absorbs photons at specific wavelengths, particularly in the ultraviolet. This absorption does not merely dim light, it removes entire spectral features. As light from early stars and galaxies travelled outward, much of it was absorbed and re-emitted at different wavelengths or scattered away entirely. This process erases fine-grained information. Detailed signatures of individual stars do not survive. What reaches us is a coarse summary. This is why early galaxies appear simpler than they may have been. Complexity existed, but it was filtered out. We need to state this clearly, because it counters a common assumption. Simplicity in observation does not imply simplicity in reality. The universe actively edits the messages it sends forward in time. This editing is not malicious or arbitrary, it follows physical laws, but the result is the same loss of detail. Now we combine these ideas. Light from early galaxies is weakened by expansion. It is filtered by intervening matter. It is sampled selectively by our instruments. It is interpreted through models built under uncertainty. None of these steps are optional. Together, they define the observational horizon. At this horizon, increasing telescope size yields diminishing returns. We can collect more photons, but we cannot recover erased information. This is the sense in which Webb looked too far, not that it crossed a forbidden line, but that it reached a regime where intuition expects clarity, and nature delivers limits. This is where disturbance arises if intuition is not prepared. We often imagine the universe as a static archive, where deeper digging reveals older layers with increasing fidelity. In reality, it is more like a dynamic system that continually overwrites its own history. Some information survives, some does not. Understanding which survives and why is central to modern cosmology. Now we pause again to stabilize. There are limits imposed by expansion. There are limits imposed by absorption. There are limits imposed by selection. Together, they define what can be known. This does not mean that knowledge collapses near these limits. It means that knowledge changes form. Instead of detailed images, we rely on statistical patterns. Instead of individual histories, we infer distributions. This shift is not a downgrade, it is an adaptation. For example, even if we cannot see individual stars from the first generation, We can infer their existence from their effects. Their radiation reionized the universe. Their deaths enriched gas with heavier elements. These consequences persist. We do not see the stars directly, like we see what they changed. This is a crucial reframing. Absence of direct observation does not imply absence of evidence. It implies indirect inference. James Webb strengthened these inferences by constraining when certain transitions must have occurred. If galaxies appear early, reionization must begin early. If reionization begins early, the first stars must ignite efficiently. This chain is logical, not speculative. Still, each link carries uncertainty. At this stage, we must resist another intuitive trap, the desire for a single explanation. Multiple scenarios can satisfy current constraints. Some emphasize rapid star formation. Others emphasize observational bias. Others adjust stellar physics. Science does not choose between them by preference. It waits for discriminating evidence. Webb provides some discrimination, not enough yet. And this is where calm becomes essential. The phrase "we don't know" enters here, but it enters with structure. We don't know the detailed properties of the first stars. We don't know the exact pace of early galaxy assembly. We don't know how representative our current samples are. We do know the boundaries within which answers must lie. These are not gaps. They are constrained spaces. Now we step back and restate what this section has rebuilt. The universe limits what information survives across time. Light is stretched, filtered, and erased by physical processes. Even perfect instruments cannot recover lost detail. Early observations are necessarily biased toward extremes. With this understanding, the disturbance introduced by Webb becomes intelligible. It is not that reality became stranger. It is that our observational window reached a regime where loss dominates. The next step follows inevitably. If information loss is fundamental, then our confidence must come not from detail, but from consistency across independent lines of evidence. We must see whether different observations' light, background radiation, large-scale structure tell compatible stories. Only then does understanding stabilize. That synthesis, and the quiet tension within it, is where we go next. Once we accept that information is filtered and erased by the universe itself, a different kind of stability becomes possible. We stop expecting clarity from any single observation and begin looking for consistency across many incomplete ones. This is how cosmology proceeds when direct access is impossible. James Webb did not operate in isolation. Its findings must be reconciled with other pillars of observation that probe the universe in entirely different ways. One of these pillars is the cosmic microwave background. This radiation does not come from stars or galaxies. It comes from a time long before either existed. When the universe first became transparent, it is uniform to extraordinary precision, with tiny variations that encode the initial conditions from which all later structure grew. These variations are small, 1 part in 100,000, but they matter. They set the amplitude of density fluctuations that gravity later amplifies. Here is the intuition that must be dismantled carefully. If early galaxies formed faster than expected, one might assume that the initial fluctuations must have been larger than we thought. But the cosmic microwave background tightly constrains those fluctuations. They are measured. They are not free to change. This constraint is powerful. It means that whatever accelerated early structure formation must operate within known initial conditions. We repeat this calmly. The universe did not start rougher than we thought. It evolved differently than we extrapolated. Another pillar is large-scale structure, the distribution of galaxies across vast cosmic volumes today. This structure reflects billions of years of gravitational growth. Its statistical properties are well measured. Any revision to early galaxy formation must still produce the structures we see now. Fast early growth cannot overshoot and create too much clustering. Slow growth cannot undershoot and leave the universe too smooth. This balance is not narrative, it is mathematical. So when Webb suggests earlier assembly, theorists do not rewrite history freely. They test whether modified formation scenarios remain consistent with the microwave background and large-scale structure. So far, no fatal inconsistency has appeared. This is important. It tells us that the disturbance is local to interpretation, not global to cosmology. We pause here to re-anchor. Different observations probe different epochs. They are independent. They constrain one another. Consistency across them is non-negotiable. This cross-checking is how confidence is earned when direct observation fails. Now consider another line of evidence chemical enrichment. Heavy elements are forged in stars and distributed by supernovae. The abundance of these elements in later galaxies encodes how many generations of stars came before. If early galaxies formed rapidly, we might expect more enrichment earlier. Observations do show heavy elements present surprisingly early, though not in conflict with existing bounds. Again, this does not close the case, it narrows it. What emerges is not contradiction, but tension distributed across multiple datasets. Each tension is mild. Together, they suggest that early star formation may have been more efficient, but not radically different in kind. This distinction matters. Efficiency can change without changing laws. Rates can accelerate without introducing new mechanisms. This is why the word disturbing must be handled carefully. The disturbance lies in expectation, not in structure. Another subtle intuition must be addressed here. We often imagine cosmic history as a single track, where all regions evolve similarly. In reality, variance matters. Some regions collapse early, others lag. Early observations may preferentially sample the former. This is called cosmic variance. It is not noise. It is real variation across space. Webb's deep fields look at narrow regions. If those regions are atypical, early impressions may exaggerate early assembly. This possibility does not undermine Webb. It contextualizes it. Again, we repeat samples are not universes. As Webb surveys expand and diversify, this variance will be quantified. Early hints will either generalize or retreat. This process takes time. It cannot be rushed without error. Now we need to stabilize again, because the accumulation of caveats can feel like retreat. It is not. The core finding remains early galaxies exist. They are bright, and they formed earlier than many expected. What remains open is how representative they are and what precise physical processes enabled them. This is the correct level of uncertainty. At this stage, we can articulate a stable frame. The early universe likely contained pockets of rapid assembly. These pockets did not violate initial conditions. They did not disrupt later structure. They exploited extreme early environments. This frame absorbs Webb's data without breaking coherence. Now we must address another intuition that often resurfaces the idea that science is uncomfortable with not knowing. In practice, science is comfortable with constrained uncertainty and uncomfortable with unconstrained stories. Webb reduced the latter and increased the former. That is progress. The next step is to understand why this progress feels psychologically unsettling. It feels unsettling because it removes a simple picture, a long, slow dawn of galaxies gradually brightening the universe. In its place, we now consider a more irregular onset, with bright islands emerging quickly in a dark sea. This picture is not scarier, but it is simply less smooth. Smoothness is something intuition prefers. Nature does not guarantee it. We pause again and restate what now feels solid. Multiple independent observations still agree on the broad outline of cosmic history. James Webb adds pressure to the early timeline, not chaos. Revisions occur within known constraints. No pillar collapses. This matters because it keeps us oriented. Now we approach another necessary transition, one driven not by data but by scale of reasoning. So far, we have treated galaxies as objects, but galaxies are emergent systems. They arise from interactions across many scales: dark matter, gas dynamics, radiation, feedback. When Webb compresses the timeline, it forces us to think less in terms of objects and more in terms of processes. Processes can accelerate under certain conditions. Objects feel static. This shift from object-based intuition to process-based reasoning is essential to remain stable. The early universe was not a quiet place waiting for complexity. It was a high-density, high-interaction environment where processes ran differently. Once we accept this, the findings stop feeling anomalous. They become signals that our mental defaults were tuned to the present, not the past. And that realization prepares us for the next descent. Because if early structure formation challenges intuition, the behavior of space itself will challenge it more deeply. To go further, we must stop thinking of space as a backdrop and start treating it as an active participant. That shift will force another replacement of intuition, one that James Webb quietly depends on, even when it does not directly reveal it. To understand why space itself matters, we need to let go of one of the most persistent intuitions we carry, that space is a fixed stage on which cosmic events play out. This intuition works locally, it fails cosmically. In the early universe, space was not just emptier or denser, it behaved differently because its expansion rate was different. Expansion is not something that happens inside space, it is something space does. We repeat this carefully. Galaxies are not moving through space away from us in the usual sense. Space between galaxies is expanding, carrying them apart. This distinction matters because expansion changes how matter encounters matter, how radiation propagates, and how structures assemble. In the early universe, everything was closer together, not just in distance, but in causal reach. Signals crossed regions faster relative to their size. Gravity connected matter more efficiently. This is where intuition built from the present misleads us. Today, expansion dominates at large scales, making distant regions effectively isolated. Early on, expansion was slower relative to density. Gravity had more time to act before separation diluted interactions. This does not mean gravity was stronger. It means its effects accumulated under different conditions. We need to restate this in another way. The same physical laws operated then as now. The background conditions were different. Those conditions altered outcomes. This is enough to explain acceleration without invoking new mechanisms. James Webb's observations force this realization into focus. If early galaxies assembled rapidly, then space itself must have facilitated efficient collapse before expansion diluted connections. This idea is not new. It is embedded in cosmological models. What changed is that Webb's data makes it unavoidable. Another intuition must now be dismantled, the idea that expansion simply pulls everything apart. In reality, expansion competes with gravity. Where gravity wins, structures form. Where expansion wins, structures freeze out. In the early universe, gravity won more often and more quickly. This is not speculation. It follows from density scaling. Density decreases as space expands. Early on, density was high. High density favors collapse. We repeat this because it feels obvious only after acceptance. Early universe high density, frequent interactions. Later universe low density, isolated systems. Once this frame is internalized, rapid early structure becomes plausible. But plausibility is not enough. We must connect this to observation again. When Webb detects a massive early galaxy, that galaxy implies an underlying dark matter halo. Dark matter dominates gravitational collapse. Baryonic matter follows. The growth of dark matter halos is well modelled. These models are constrained by the cosmic microwave background and large-scale structure. They predict that some halos collapse early and grow quickly. These early halos are rare but not forbidden. If galaxies form preferentially in these early collapsing halos, then early massive galaxies become expected outliers, not contradictions. Again, We repeat outliers are not errors if the distribution allows them. The tension then shifts from how is this possible to how common is this. This is a subtle but stabilizing shift. Now we examine another piece of intuition that must be replaced: the idea that cosmic history unfolds uniformly everywhere. In reality, cosmic time is global, but cosmic experience is local. Different regions of the universe experienced ionization at different times. Some lit up early, others remained dark longer. Webb's view is biased toward early lit regions because those are the ones whose light could escape. This introduces a temporal bias layered on top of spatial bias. Again, we repeat because it matters. We see regions that formed early because only early forming regions are visible early. This circularity is not a flaw, it is a selection effect to be modelled. Understanding this removes another source of disturbance. Now we pause to re-anchor. Space is dynamic, not static. Early conditions favoured rapid interaction. Gravity competed more effectively with expansion. Early structure can emerge quickly without new physics. This frame absorbs much of the shock. However, there remains a deeper discomfort that has not yet been addressed. It is not about galaxies. It is about our sense of chronology. We are used to thinking of time as flowing uniformly, with equal importance at every moment. Cosmic history does not respect this intuition. Some epochs matter more because conditions change rapidly, others stretch quietly. The early universe was an epoch of rapid change. Small increments of time carried large consequences. This compresses causal chains. Processes that take billions of years today may have unfolded in hundreds of millions then. Again, we repeat because this reframing is essential. Time is not uniform in consequence. Equal durations do not imply equal change. Once this is accepted, the idea of an early fast assembly no longer feels unnatural. It feels like a miscalibrated expectation corrected by data. Now we return briefly to James Webb, not as a discoverer of anomalies, but as a confirmer of this regime. Webb did not create early galaxies. It revealed that our previous instruments were blind to them. This blindness shaped intuition. Now that it is lifted, intuition must adapt. This adaptation is uncomfortable only if we resist it. The final intuition we dismantle in this section concerns scale separation. We like to believe that processes at different scales are cleanly separable. In cosmology, they are not. Star formation depends on gas physics. Gas physics depends on halo growth. Halo growth depends on expansion. Expansion depends on energy content. These layers interact. Changing conditions at one level propagates upward. Early expansion rates, densities, and radiation backgrounds altered star formation efficiency. That altered galaxy assembly. That altered ionization. This chain is not linear, it is coupled. James Webb's findings force us to confront this coupling more directly. We pause one last time to restate where we stand. Early galaxies forming quickly do not imply broken laws. They imply that coupled processes operated under extreme conditions. Our previous intuition underestimated how different those conditions were. Webb corrected that underestimation. With this understanding, the phrase "look too far" takes on its true meaning. Webb did not cross a forbidden boundary, it crossed a cognitive one. It reached a regime where our default mental models built from the nearby, the recent, and the slow stopped being reliable. And beyond that point, we must proceed with rebuilt intuition. The next step in this descent is unavoidable. If space itself participates in structure formation, then our assumptions about measurement, distance, and age require further adjustment. Because expansion does not only affect how things form, it affects how we measure how far and how old they are. And that, quietly, is where some of the most persistent confusion hides. Distance feels like one of the most stable concepts we have. We imagine it as a ruler laid across space, marking how far apart things are. This intuition works on Earth. It breaks down cosmologically. In an expanding universe, distance is not a single quantity. It depends on when you measure it, how you measure it, and what you mean by far. This is not philosophical subtlety. It is a practical problem that affects every claim about early galaxies. When we say a galaxy is 13 billion light-years away, we are compressing several different distances into one phrase. Light travel distance, proper distance at emission, proper distance now, these are not the same. We need to slow down here, because this is where intuition fails quietly and persistently. Light travel distance tells us how long the light has been travelling. 13 billion years means the light left when the universe was very young. But during those 13 billion years, space expanded. The galaxy is now much farther away than 13 billion light-years in any static sense. Its current proper distance is far larger. This matters because expansion changes the relationship between distance and time. We cannot imagine light simply crossing a fixed gap. The gap itself stretches while light is in transit. We repeat this carefully. The photon does not race across a static void. The void grows beneath it. Arrival time encodes expansion history, not just separation. Once this is accepted, a second intuition must be dismantled, the idea that redshift directly equals velocity. At small distances, we can interpret redshift as motion. Farther away, this interpretation fails. The redshift of very distant galaxies is dominated by expansion of space, not motion through space. This distinction matters because velocity implies kinetic history. Expansion implies geometry. James Webb observes extremely high redshifts. These redshifts tell us that the light was emitted when the universe was much smaller. But converting redshift into age requires a cosmological model. That model includes assumptions about expansion rate, matter density, and dark energy. These assumptions are well tested, but they are not trivial. So when Webb identifies a galaxy at a redshift corresponding to a certain cosmic age, that age is not read off directly, it is inferred. Again, we repeat age estimates are model-dependent. This does not mean they are unreliable, it means they are conditional. The disturbance arises when people hear this galaxy existed 300 million years after the Big Bang and imagine a precise timestamp. In reality, this is a range derived from a model that fits multiple datasets. Within that range, early galaxies still appear surprisingly developed. So the core tension survives refinement. Now we need to address a deeper intuition failure, the idea that cosmic age is a global clock ticking uniformly everywhere. Cosmic time is defined relative to the expansion of the universe, not to local processes. It is a coordinate, not an experience. Two regions of the universe at the same cosmic time can look very different depending on density, environment, and history. This means that early does not mean primitive in a universal sense. It means young relative to expansion, not undeveloped. This distinction matters because it dissolves another layer of surprise. Early galaxies need not resemble small versions of modern ones. They can be different in kind. James Webb's observations suggest this may be the case. Now we pause and re-anchor. Distance in cosmology is not singular. Redshift encodes expansion, not simple motion. Age estimates rely on models constrained by multiple observations. Early does not mean uniform. With this frame, we can revisit mass estimates calmly. When astronomers say an early galaxy appears too massive, they mean too massive relative to expectations derived from simplified growth models. But those expectations assume certain distances, luminosities, and stellar properties. As distance measures refine, some mass estimates soften, others persist. This is not retreat, it is calibration. Another subtle point must be addressed here: the role of lensing. Gravitational lensing occurs when massive objects bend space-time, magnifying light from background sources. Webb observes many galaxies through natural cosmic lenses. This magnification can make galaxies appear brighter and larger than they are. Correcting for lensing requires modelling the foreground mass distribution. These corrections are improving, but they add another layer of inference. Again, we repeat because intuition demands simplicity. Brightness does not equal mass. Distance does not equal age. Observation does not equal direct measurement. All of these equivalences fail at cosmic scales. Yet despite these failures, coherence remains. Multiple teams, using different methods, still find early galaxies assembling faster than naive intuition predicted. This persistence matters. Now we confront a potential misinterpretation that often surfaces the idea that if distance and age are model dependent, then anything goes. This is false. Cosmological models are tightly constrained. Changing one parameter affects many predictions. Only certain combinations remain viable. James Webb's data sits inside this constrained space. It nudges boundaries. It does not dissolve them. We pause again to stabilize. Uncertainty here is structured. Constraints are interlocking. Freedom is limited. This is why the disturbance is subtle. It does not announce itself as a contradiction. It accumulates as discomfort with simplified stories. Now we need to address how this discomfort propagates psychologically. Our brains prefer spatial metaphors. We imagine looking farther as seeing more distant places. Cosmology forces us to imagine looking farther as seeing earlier times. This inversion is already difficult. Adding expansion and multiple distance measures compounds the strain. James Webb operates precisely where this strain peaks. It shows us objects whose light began its journey when the universe was radically different, and whose current separation is far greater than their light travel distance suggests. Holding these facts simultaneously is cognitively demanding. So we simplify, and in simplifying we generate false expectations. Webb's findings correct those expectations. The correction feels like disturbance only because the simplification felt comfortable. We now restate what intuition must carry forward. Looking farther is looking earlier. Earlier does not mean simpler. Distance is dynamic. Age is model-derived. With this rebuilt intuition, we can approach the remaining tension without destabilization. Because beyond distance and age lies an even deeper challenge. It concerns not where or when early galaxies exist, but how confidently we can say what they are made of. Composition, not position, is the next frontier. And it is here that light again will resist our desire for clarity. Composition feels tangible. We're used to thinking that if we know what something is made of, we know what it is. In cosmology, composition is inferred, not sampled. And the further back we look, the thinner that inference becomes. When James Webb observes an early galaxy, it does not detect atoms directly. It detects how collections of atoms interacted with radiation billions of years ago. From this interaction, we infer chemical makeup. This inference relies on spectral lines. Each element absorbs and emits light at specific wavelengths. In nearby stars and galaxies, these patterns are well calibrated. We have ground truth. In the early universe, we do not. The first generations of stars formed from almost pure hydrogen and helium. Heavy elements were absent. Their spectral behavior is expected to differ from modern stellar populations. This introduces a problem. If we use modern templates to interpret ancient light, we may misclassify what we see. This is not speculation. It is a recognized limitation. James Webb pushes us into a regime where this limitation becomes consequential. When early galaxies appear bright, we often interpret that brightness as evidence of high stellar mass. But brightness also depends on stellar composition. Metal-poor stars burn hotter and brighter per unit mass. If early stars were metal-poor and they were then a given brightness corresponds to less mass than it would today, this reduces tension, but it does not eliminate it entirely. Again, we repeat composition alters interpretation. The challenge is that we do not know the precise stellar initial mass function in the early universe. This function describes the distribution of stellar masses at birth. It affects luminosity, lifetime, and chemical output. If early stars were biased toward higher masses, galaxies would appear brighter without requiring enormous mass buildup. This is plausible, but it must be constrained. James Webb provides some constraints, but not definitive ones. Now we pause to re-anchor. Spectra encode composition indirectly. Templates are extrapolated, not measured. Metallicity alters luminosity. Stellar populations matter. With this frame, we can examine why composition is such a sensitive lever. Consider two galaxies with identical stellar mass. One has metal-rich stars, the other has metal-poor stars. The metal-poor galaxy emits more ultraviolet light. After redshift, this light appears as enhanced infrared brightness. If we misattribute this brightness to mass rather than composition, we overestimate how much material assembled early. This effect is not trivial. It can shift mass estimates by factors of several. This is one reason why early excitement about extremely massive early galaxies has been tempered by subsequent analysis. But again, tempering does not erase the finding. Even conservative interpretations still imply rapid star formation. Now we examine another compositional aspect: dust. Dust absorbs and re-emits light. In nearby galaxies, dust complicates interpretation. In early galaxies, dust formation itself is uncertain. Dust requires heavy elements. It forms in stellar winds and supernovae. Early on, heavy elements were scarce, but massive stars can enrich environments quickly. If dust formed early, it could redden spectra, mimicking older stellar populations. James Webb's sensitivity allows detection of dust signatures earlier than before. This is itself surprising. The presence of dust early implies rapid cycles of star formation and death. Again, this compresses timelines. We repeat this carefully. Dust implies previous stars. Previous stars imply earlier formation. Earlier formation implies efficiency. Each link adds pressure. At the same time, dust complicates age estimates. Reddened light can appear older than it is. This dual role makes dust both an indicator and a confounder. This is why interpretation must be iterative. Now we need to address a deeper intuition failure, the idea that composition evolves smoothly over time. In reality, chemical enrichment can be punctuated. Massive stars live short lives and enrich their surroundings quickly. Early environments may have experienced rapid jumps in composition. This punctuated enrichment undermines linear extrapolation. James Webb's findings are consistent with such behavior. Now we pause again to restate where understanding stands. Early galaxies may appear massive partly because their stars are brighter. Metallicity and dust alter spectra in competing ways. Compositional uncertainty remains significant, yet even conservative models allow rapid early assembly. This last point matters. Even after adjusting for composition, early galaxies are not slow. The disturbance persists, but it is refined. Now we need to confront the most unsettling compositional question: the first stars themselves. These stars are hypothetical. They have not been observed directly. They are called population 3 stars. They are expected to be massive, hot, and short-lived. Their light may be difficult to detect directly, but their effects shape everything that follows. James Webb has not definitively detected population 3 stars. It may never do so directly. This absence is not failure, it is expected. Population 3 stars likely lived and died before the universe became transparent enough for their light to escape widely. We infer their existence from chemical signatures, not images. This reinforces a pattern we have seen repeatedly. The earliest phases of cosmic history leave indirect traces, not direct records. James Webb sharpens some of those traces. It does not conjure images where none can exist. This understanding stabilizes the narrative. Now we pause one last time to consolidate. Composition is inferred through models layered on light. Early conditions differ radically from modern ones. Assumptions must be re-examined. Even after revision, early structure remains rapid. With this rebuilt intuition, the phrase "look too far" no longer suggests error. It suggests contact with a regime where inference is delicate. We are not seeing contradictions, we are seeing sensitivity. Sensitivity to assumptions, sensitivity to conditions, sensitivity to scale. And that sensitivity is not a weakness. It is a signal that we are approaching fundamental limits of observational cosmology. The next step is to confront those limits directly. Not in terms of technology, but in terms of what the universe allows to be known at all. Because beyond composition lies a boundary that no telescope can cross, no matter how powerful. And understanding that boundary is what finally grounds the disturbance. There is a limit that does not soften with better instruments or refined models. It is not a technical horizon. It is a causal one. Beyond it, information does not merely become hard to interpret, it never arrives. To understand this limit, we need to confront the idea of horizons not as metaphors, but as physical boundaries imposed by the structure of space-time. The universe has an observable horizon. This horizon marks the maximum distance from which light has had time to reach us since the beginning of cosmic expansion. Anything beyond it is not hidden. It is causally disconnected. This is not a temporary restriction. It is permanent. We repeat this carefully because intuition resists it. Some regions of the universe will never be observable. No future telescope will see them. No signal from them can ever arrive. This is not pessimism. It is geometry. James Webb operates entirely within this horizon. It approaches its inner edge, but it does not cross it. The disturbance it introduces comes from nearing a boundary, where information density thins and inference replaces observation. Now we need to distinguish this horizon from another one that often causes confusion, the event horizon of cosmic expansion. Because the universe's expansion is accelerating, there are regions that are currently observable but will eventually slip beyond our reach. Light emitted from them in the future will never reach us. This means that the observable universe is not static. It is dynamic, shrinking in causal terms even as it grows in size. Again, we repeat, some things we see now are the last signals we will ever receive from them. Future information from those regions is already lost. This realization reframes what looking far means. When James Webb observes very distant galaxies, it is not just looking back in time, it is intercepting signals near the edge of what can ever be known. This is not dramatic, it is a quiet fact. Now we pause to stabilize. There are hard causal limits on observation. They are imposed by space-time, not technology. Approaching them increases uncertainty by necessity. This understanding protects us from over-interpreting tension as crisis. Now consider what this implies for the earliest epochs. Even in principle, we cannot observe the universe before certain transitions. The cosmic microwave background marks one such limit. Before it, light could not travel freely. This boundary is absolute. James Webb cannot see beyond it. No telescope can. So when we ask about the first stars, the first galaxies, or the onset of structure, we are already operating near a fundamental wall. What Webb does is refine the location and texture of that wall from one side. It does not breach it. This matters because it clarifies the role of unknowns. There are unknowns we can reduce with better data. There are unknowns we can never eliminate. Confusing the two leads to instability. The disturbance surrounding Webb often arises from treating the latter as if they were the former. Now we examine another intuition that must be dismantled, the idea that horizons imply ignorance in a human sense. In reality, horizons imply completeness in a scientific sense. They define the domain of possible observation. Within that domain, we can build consistent models. Beyond it, speculation is unconstrained. Science stops at the horizon not because curiosity ends, but because evidence does. This is not a limitation of imagination. It is a discipline of method. James Webb sharpened this discipline by pushing observation to where evidence thins. Now we need to confront a subtle consequence of horizons. Cosmic variance becomes unavoidable. Because we observe only a finite region, our universe is one realization of a statistical ensemble. Other regions beyond the horizon may differ, but we will never know. This does not weaken cosmology, it defines its scope. All cosmological claims are conditional on what is observable. James Webb does not change this, it reminds us of it. Now we pause again to restate what is solid. There are absolute observational limits. They are well understood. They do not invalidate inference within them. They prevent overreach beyond them. This frame is stabilizing. Now we address the emotional misinterpretation that often accompanies talk of limits. Limits are not failures, they are structures. In physics, knowing where measurement ends is as important as knowing where it works. James Webb's contribution is not that it revealed chaos, but that it revealed proximity to boundary conditions. At boundaries, intuition breaks, models strain, uncertainty grows. This is expected. Now we return to the phrase looked too far, not as accusation, but as description. Webb looked far enough that our simplifying assumptions about pace, composition, distance, and chronology could no longer hide behind data scarcity. It forced us to confront how much of our confidence was built on extrapolation. This confrontation is uncomfortable only if we mistake extrapolation for observation. Science does not. Now we take a final pause in this section to consolidate. The universe imposes hard causal horizons. Approaching them increases reliance on models. James Webb operates near these limits. Disturbance arises from intuition meeting boundary. With this understanding, we can finally place Webb's findings in their proper context. They are not revelations of impossibility. They are exposures of where certainty gives way to structure-bound uncertainty. The last step in our descent will not introduce new data. It will return us to the opening intuition that seeing means knowing, and rebuild it one final time, in a form that can survive these limits. Because understanding the universe is not about eliminating uncertainty. It is about living stably inside it. By now, the idea that seeing equals knowing has been dismantled repeatedly. But dismantling is not the goal. Replacement is. We need a new intuition that can hold under extreme scale, near causal boundaries, and inside permanent uncertainty. This new intuition begins with a quiet shift. Observation is not access to reality itself, but access to constraints on reality. James Webb does not show us what the early universe was like in a direct sense. It shows us what the early universe could not have been. This distinction matters. Before Webb, many slow formation scenarios were comfortable simply because no data excluded them. After Webb, some of those scenarios are no longer viable, not because Webb disproved them individually, but because the collective pattern of observation makes them increasingly implausible. This is how knowledge advances at the edge. We do not gain pictures, we gain exclusions, and exclusions reshape understanding. This is counterintuitive, because we associate learning with accumulation. At cosmic limits, learning happens through elimination. We repeat this because it is easy to miss. The most important result is often what can no longer be true. James Webb's disturbance lies precisely here. It removed the comfort of vague timelines and replaced them with constrained ones. Now we must stabilize this idea because it can feel like loss. It is not. Constraints are not restrictions on imagination. They are supports for reasoning. A model that survives more constraints is stronger, not weaker. Now consider how this reframing resolves many earlier tensions. Early galaxies appear massive. That rules out the slowest assembly paths. They appear early. That rules out delayed star formation. They appear repeatedly. That rules out singular flukes. What remains is a narrower family of histories that fit all observations simultaneously. This narrowing is not dramatic. It is quiet, technical, and cumulative. And it is exactly what science aims for. Now we address a lingering intuition failure, the expectation of finality. People often ask whether Webb proved something was wrong. This question assumes that science aims for definitive closure. In reality, science aims for resilient frameworks. James Webb did not close questions, it hardened them. It made them precise enough to resist vague answers. This is progress. We pause again to re-anchor. Seeing does not equal knowing. Knowing means constraining. Constraints accumulate. Understanding stabilizes. With this frame, the word disturbing loses its emotional charge. It becomes descriptive. Disturbing means that a comfortable but weak intuition was replaced by an uncomfortable but stronger one. Now we must address one more subtle but important aspect: trust. At the edge of observation, trust shifts from individual data points to coherence across independent lines. No single Webb image carries decisive weight. Its power comes from consistency with other Webb images, with background radiation, with large-scale structure, with chemical abundances. This coherence is what allows us to remain calm. If Webb's findings had contradicted other pillars, alarm would be justified. They did not. They applied pressure locally, not globally. We repeat this because it is stabilizing. No pillar of cosmology collapsed. No law was violated. Adjustments occurred within structure. This is what healthy science looks like at scale. Now we confront another intuition that must be replaced: the idea that uncertainty diminishes with time. In some domains, uncertainty grows as we approach boundaries. This is not failure, it is geometry. James Webb operates where diminishing returns are expected. Each additional photon carries less new information. Yet those photons still matter because they refine constraints. This is the regime we are now in. The future of early universe observation will not deliver clarity in the everyday sense. It will deliver tighter limits, smaller error bars, and fewer viable histories. This is a different kind of progress. Now we pause to restate the rebuilt intuition fully. Looking farther means intercepting weaker, older, more filtered signals. Those signals do not reveal detail. They reveal structure through consistency. Knowledge emerges from coherence, not immediacy. With this intuition in place, the narrative surrounding James Webb settles. It did not look too far in the sense of overreaching. It looked far enough that our informal reasoning stopped working. It forced us to replace intuition with discipline. This is not a dramatic moment in science. It is a typical one at the frontier. What makes it feel unusual is its visibility. Webb's images are public. The adjustments are visible. The discomfort is shared. Now we must prepare for the final descent. The ending will not introduce new discoveries. It will not escalate scale further. Instead, it will return us to the opening idealite, seeing and understanding, and place it in its final, stable form. Before that, we pause one last time in this section to consolidate. James Webb revealed limits, not impossibilities. It refined timelines, not laws. It forced intuition to mature. Understanding became quieter, not louder. With this frame, we are ready to end without resolution, because resolution was never the goal. Stability was, and that stability now rests on something stronger than vision. It rests on constraint. Tonight, we began with something familiar light, not as an abstraction, but as the quiet mechanism behind seeing. We treated it as something simple, because at human scales it behaves that way. And then, step by step, that intuition failed. So we end by rebuilding it one last time, not as comfort, but as something stable. Light does not show us the universe as it is, it shows us what survives the journey. This sentence now carries weight that it did not at the beginning. Every photon James Webb detects is not a messenger from the present. It is a survivor from the past. It has crossed expanding space, lost energy, passed through absorbing matter, and arrived carrying only what could not be erased. That is not a flaw in observation. That is the nature of observation at cosmic scale. When Webb revealed early galaxies that appeared bright, massive, and structured, the disturbance was never about impossibility. It was about pace, about how quickly complexity can arise when conditions are extreme. What felt unsettling was not the data. It was the quiet realization that our default expectations were built from the nearby universe and projected outward without sufficient caution. Once that projection failed, nothing collapsed, it adjusted. We learned that early does not mean simple, that far does not mean slow, that seeing does not mean direct access. We learned that the universe edits its own history as it expands. Information fades, detail is lost, only certain signals endure. And we learned that this loss is not random, it is structured. Because of that structure, we can still reason. James Webb did not reveal chaos, it revealed constraint. It showed us that some histories are no longer plausible, that some timelines are too slow, that some intuitions were too smooth. What remains is not confusion, but a narrower space of understanding. This is the reality of working near horizons. As we approach the limits set by space-time itself, knowledge does not arrive as clarity, it arrives as exclusion. We learn what cannot be true. This feels unsatisfying only if we expect answers to look like images. In cosmology, answers look like coherence. Across everything we examined, light, expansion, distance, composition, formation. One pattern held, independent observations still agree, no pillar fractured, no law bent. The universe did not become stranger, our picture of it became less naive. That is the quiet achievement. So when we say that James Webb looked too far, we now understand what that means. It looked far enough that intuition built for human scales could no longer hide behind familiarity. It looked far enough that seeing stopped feeling like knowing. And in that moment, understanding had to be rebuilt deliberately. This is not a dramatic ending, it is a stable one. Because the universe does not resolve into stories, it resolves into constraints. And those constraints are not a barrier to understanding, they are its foundation. We live in a universe where some things can be known, some things can be inferred, and some things will never send us information at all. James Webb did not change that structure. It clarified where we stand inside it. We understand now that looking deeper will not bring closure, it will bring refinement. Future observations will not overturn everything we know, they will narrow it. And that narrowing will feel, again and again, like disturbance only if we forget what understanding actually is. This is the reality we live in. We understand it better now, and the work continues.